crucial moments do they pay attention carefully?
Welcome to Some Easy World Science channel. In this video, this should be the fourth class on the JAMB chemistry free classes. Fourth class, which is handling second topic. We are done with the first topic. We move into the next topic, but this is going to be the period one, the first period in the first topic. And we come over here to see the next topic. In our last upload, we discussed separating techniques. So we are looking at this chemical combination. In this video, we can finish it in just this period one. So we're going to start from the laws of chemical combination. We'll treat this law of definite proportion and eventually stop at Gay-Lussac's law of combining volume. In second class, we will handle the other. So happy watching, and don't forget to ask your questions in the comment section. So if you are finding any of these calculations or these laws difficult, you stay patient for us to discuss all of them. We will look at the aims and objective. From the objective, they say students should be able to perform simple calculations. So it's all about the law and the little calculations that follow it. So our topic is going to be, this should be chemical combination. It's all about chemical bonding, but we have to look at the laws governing the combination of atoms together, and then so look at laws of chemical combinations. Remember, I will answer questions, UTME questions. So we will follow them one after the other. Law of definite proportion. So this law of definite proportion is also called, you can also call it law of constant composition. So, and then the next law according to them should be law of multiple proportion. If you look at it here, law of multiple proportion and law of conservation of mass. Law of conservation of mass or matter. I think they use matter there. Okay, matter. And finally, Lusac's law of combining volume. Okay, now for your own interest, there is already a live stream on this law in detail, about an hour live stream on Lusac's law of combining volume on this channel. So endeavor to search for it and watch. Let me go with the first one, which is the law of definite proportion. So on this aspect, law of definite proportion is telling us that maybe and change to black. So we start with it states that all pure samples of the same compound contains same element in fixed proportions by mass, irrespective of the source or the method of preparation, or the method of preparation of such salt. This implies that I want to take sodium chloride, for example. There are many approaches you can apply in producing sodium chloride. To explain this law, let's take a look at sodium chloride. This is all about having different ways of preparation of one particular compound. So one can prepare sodium chloride in the lab. One can also get it as a rock salt or a sea salt. So whichever way you get this sodium chloride, provided that this sodium chloride is pure, it will always contain sodium and chlorine combined in fixed ratio by mass of 23 grams of what? Sodium to 35.5 grams of chlorine. That's the law of definite proportion. So, and the same thing, bringing water that we know, anything called water must, no matter the source, whether you produce it by sparking of hydrogen and eventually condensing it back, you get water combined. Having hydrogen in fixed ratio by mass of 2 grams of hydrogen will always combine with what? 16 grams of oxygen if it is pure. So any source you use to make water, whether it's seawater, rock, river, ocean, as far as you purify it, remember we're talking about pure samples. Look at the question, look at the definition. Pure samples, they contain the same element in fixed ratio by mass. So there is nothing that actually will make it change. Now, let me go back to the sodium chloride I've been using. One can produce sodium chloride by reacting a base, sodium hydroxide, with an acid to give sodium chloride plus water. If you purify this sodium chloride, it is the same thing as somebody else might decide to spark sodium metal in stream of chlorine gas to get sodium chloride. As far as these are pure samples, they will always have the same mass of sodium and chlorine in fixed ratio by mass. So remember, for example, water, if you ever try to combine 2 grams of hydrogen with what? 32 grams of oxygen. This is no more water. This is not water again, but what? This is no more water, but hydrogen peroxide, and is a different compound altogether. So for you to call it water, it must contain hydrogen and oxygen in fixed ratio by mass. It doesn't change. No matter the method of preparation you apply, remember it must be purified. Understood? So there is this law of constant composition. So for you to understand this, let's take for example, if we say a compound that contains take for example, a question might ask you, what if a compound contains 27 grams of aluminium and together with 70, okay, let's check from the calculator department. If we say chlorine 35.5 times 3, 35.5 times 3 is 106.5. If a sample contains 27 gram of aluminium and 106.5 grams of what? Chlorine gas, and another sample was found to contain 54 grams of aluminium, and we also have about 213, maybe, okay, 213, okay, I'm right, 213 grams of chlorine. This is still showing constant composition. How will you know it? We have two elements which are aluminum and chlorine. You take the ratio of their masses. So how will you take the ratio of their masses? Always I start in the middle. So permit me to highlight this and move it up. Yeah, so that I can have space to write. Yeah. So in this case, you take the ratio of mass of aluminium to that of what? Chlorine, just Al over Cl. In the first case, case A and case B. See, in case A, what's the mass of aluminium? 27 over mass of chlorine, 106.5. You will get our answer. Then in the case of B, what do we have? 54 all over 213. We are expected to get the same thing. That shows constant composition. Okay. So let's see, 27 divided by 106.5 is 0.253. 0.25. So here we have 0.25. Then 54 divided by 213 is still 0.25. You see, that's law of definite proportion. 0.25. Sorry. So they are equal. Okay. So let's look at some examples here and solve one example I lifted and check what law is obeying. Okay, this should be JAMB question 1991, question number 4. Okay, I gotta zoom it in for you to see well. Question number 4 says in two separate experiments, 0 point, look at it, 0 point, in two separate experiments over here. Let me use this 0.36 gram and 0.71 gram all chlorine combined with a metal X to give compounds Y and Z. Remember, Y and Z are compounds respectively. On analysis, they discovered that this Y contained 0.2 grams and this Z contains 0.4 grams of X respectively. So they now say the data above represents the law of what? You are going to solve this. You are going to solve this. So through the solving, you will know the law it actually represents. Understood? So we are going to take a look at the ratios. The ratio of the mass. I think I'm going to minimize this and we continue solving. I hope we can still recall. Remember, it was 0.36 grams and 0.71 grams, all of what? Chlorine. Then reacted with X, that means we have XCl, and then we also have a Y. They form the compound Y. Maybe we take the X and Y was used to represent different compounds, but that doesn't mean we're going to still. It's going to be XCl. Okay, why this one can be referred to as Y compound and this is the Z compound. You see what I mean? So we will take their proportions. X remained constant, but they later told us the masses of X. In the first instance, over here, what is the X? Because it was later mentioned. In Y, it contains 0.2 grams of X. Is the ratio of what? 0.36. 0.36 grams of chlorine. That is it. Now, in the case of B, maybe I shift this a bit, shift this and do the same thing. In the case of Z, what happened? It is 0.4 grams of the metal X will give us reacted with 0.71 gram of chlorine. So remember when I talked about aluminum chloride, we will take the mass ratios X over Cl here and X over Cl here. So interpreting the 0.2 over 0.36, here should be 0.4 over 0.71. So let's check what it will give us. 0.2 over 0.36 from calculator department. We have 0.5, 0.55 in each case. Okay, I have 0.55, which is approximately 0.56. So let's go here. If we get the same value again, if we get 0.56 again here, that is law of definite proportion. No two ways about it. Okay, 0.4 divided by 0.71, we have 0.563, which is approximately the same thing. So 0.56. So it's law of what? Definite proportion or constant composition. That's the answer to the question. Remember, I took X over Cl. I can also do Cl, ratio of mass of chlorine to mass of the metal. Over here, what matters is what you do on this compound, you do it the same way. So if we do the ratio, it will still give us the same thing. To give us the same fixed mass. That's law of definite what? Proportion. I think permit me now to move on to the next one, which is law of multiple proportion. Let's remove this and clean off. Remember to ask your questions. You are on with Sa Majesty's World. Your exam success is my topmost priority. So endeavor to please subscribe to this channel, please. If you love what I'm doing and you want to expand this community, just subscribe and please, I am begging you, please share this video to help others if you have gotten any help at all. Then like, also give us thumbs up. It will encourage us to do more. Or do you want me to stop? I know you don't want me to stop. Thank you. God bless you. Now let's move to the next law, which is law of multiple proportion. Law of multiple proportion. Okay. This law states that when two elements states that when two elements A and B combines to form more than one compound, that one of them will have a fixed mass, that the variable masses of one will vary, one will be fixed, that the variable masses of, if you like, if you say A of A, that reacts or that will react with the fixed mass of B are in simple whole number ratio, are in simple whole are in simple multiple ratio, sorry, are in simple multiple ratio. Let's use multiple ratio. Are in simple multiple ratio. So that's this law. Let me explain for your understanding. It is talking about two elements forming more than one compound, and in this case one will have a variable mass. It is now considering, remember the law of definite proportion is considering one compound. It's not two, even though I have used two compounds in the other case. It's just one compound, but with different proportions. The different proportion says it's just like if you measure 2:4. Remember, when here is 4, is make it 8. That's definite proportion or constant composition. If here becomes 16, 32. But this time around, the law of definite proportion is checking how one is varying. The one that have a varying mass, how much, in what pattern are they varying? In the pattern of multiples, not just in point. Like if you are 2, the next one, the other one will be 4, then the other one will be 6. You see, it's now in the multiples of 2. So this is better understood when I give you example. Just calm down. Let me show you something. For example to this is, let's consider carbon. I want to give you two examples: carbon and oxygen. The next example is copper and the same oxygen. These two forms more than one compound in a different way with different ratios. So now let's see carbon, the example 1. In the EG1, carbon can react with one atom of oxygen to form carbon monoxide or carbon dioxide. The same carbon can react with two atoms of oxygen to form carbon dioxide. My dear, if you look at this, you find out that one carbon here, but one oxygen here, two oxygen here. Are you seeing what is happening? 1:2 in a simple ratio, because 1 times 2 now is 2. Not that here will be 1 and here will be 1.5. No, it's not a multiple. If here is 2, here is expected to be 4, because the multiple of 2 is 4 in multiple ratio. Now, carbon, the mass of carbon here is fixed, but oxygen is varying in the two cases. Let us do the mass. In CO, what is the mass? 12 grams of carbon reacted with what? With 16 grams oxygen. Then in CO2, what do we have there? The same 12 grams, that is 12 grams, that is fixed mass, now combined with what? Oxygen here is 2 in CO2. In CO2, oxygen is 2. So 2 times 16 is 32 grams. So the law is trying to tell us now that the variable masses of the second element, that is this, are you seeing it now, is fixed. It's just a simple multiple ratio. It cannot just be any number. So this is 16:32. When you break it down, it becomes 1:2. If you take the lowest ratio, 16/32, will give you 1/2, which is 1:2. So it cannot, this place cannot be 16 and here will be 28, because 28 is in no way a multiple of 16. So if here is 16, here is allowed to be 64. Is allowed. Here can be 64. Do you know why? Because 64 is a multiple of 16. 16 times 4 is 64. It is also possible that this can be 48. But what is not possible is that this can become just 30, or this can just become 25. 25 is in no way a multiple of what? 16. So that's the law. We go to example 2, which is copper now and what? Oxygen. In copper and oxygen, we are going to see a similar but a slightly different from the other case. In copper and oxygen can form two compounds. This time around, copper oxide and what? Copper 2 oxide and copper 1 oxide. See now, if you watch this case, which one is fixed? The mass of copper 2 oxide and mass of copper 1 is not the same, but there is an element that have equal contribution in masses. Let's do it the other way. At least you see that copper here is one atom, oxygen here is one atom, copper here is two atom, oxygen here is one atom. So which one is fixed? Which one remained one? It is oxygen remained one here. In our first example, oxygen was varying, but in this case now, oxygen is the fixed mass. Okay, so let's do it like we did in the other one. In CuO, what happened? 64 grams. 64 is the molar mass of carbon to be given to you in exam. 64 grams copper combined with 16 grams of what? Oxygen. And then in copper 1 oxide, sorry, remember Cu2 plus is copper 1, not Cu2 plus, please. Cu2O is copper 1. This is copper 1. The oxidation state of copper here is plus 1, while the oxidation state of copper is plus 2. That makes you a chemist. Now we move on. If we continue this, what do we have? We now have 64 here times this 128 grams copper still combined with 16 grams of what? Oxygen. You see, 16 is now fixed. What is varying? Copper. And if you look the ratio, 64 and 128. 64 and 128. If you have 64 is to 128, it is still in the simple multiple ratio of 1 is to 2. So if 64, you multiply by it, you get 128. So that is it for law of what? Multiple proportions. Most times, if this question if you find it difficult to answer which law is being represented, if you see any question that mention two elements, maybe they called copper, they now called oxygen. Most times, you can just go for law of multiple proportion. But I did not say always. Maybe we can take a look at some questions concerning this law and we move to the next. All pure number 4 says all pure samples of the same chemical compound contain the same element in the same proportion by mass is a statement of is law of constant composition or law of definite proportion. So option B have it. But look at question number 2. Even that number 1, even though it's trying to confuse you, that number 1 had X oxides whereby X varied. You are going to be comparing two compounds here because that's the only one that we can measure their ratio. If you say XO XO and XO2. X is constant and oxygen is varying and is varying in the ratio of 1 is to 2. Then if you consider X2O and XO, oxygen becomes constant and X is varying and is varying in 1 is to 2. Still simple ratio. So the answer to this is law of multiple proportion, which is option D. Then option number 2 says a metal M forms two types of chlorine. We have done this MCl2 and MCl3. Are you seeing that M is constant here, but chlorine is now 2 and 3? The thing there is that if you look at, it's still in that ratio, multiple of one another. Though you cannot tell me that 2 times 3, 2 times 2 is 3, no. But it's in the multiple of one constant, which is this chlorine. If chlorine is 35.5, 35.5 times 2 is 71. Then 35.5 times 3 is 106.5. Are you seeing it? So it's in the multiple of one particular number. So this started from 1 is to 2 is to 3. So it's in a simple whole number ratio. So don't get it twisted. This is still law of what? Multiple proportion. But the options don't even, okay, have it, that's option C. Okay, so this is it for law of multiple proportion. We go to law of conservation of mass.
Learn science for free with Sir Majesty Easy World Science. Master chemistry, biology, and physics on our YouTube channel, where we offer comprehensive tutorials, exclusive science practical demonstrations, real-world applications of scientific knowledge to solve environmental and human challenges. We also specialize in building and equipping science laboratories with quality and reliable services. Call WhatsApp +234 706 516 6217. Join us and elevate your learning experience. Stay majestic.
So the next law is law of conservation of matter. Sorry. So law as number 3 of conservation of matter. So law of conservation of matter says that matter is neither created nor destroyed, or can be matter can neither be created nor destroyed, but can be transformed from one form to another. That's the law of conservation of matter, which is equivalent to the law of conservation of mass. So when we talk about law of conservation of matter, what makes up matter is atoms, molecules, ions, mostly is atoms. So according to uh, uh, according to according to Dalton, one of his theories is that atoms can neither be created nor destroyed, which is true. Then Anton Lavoisier also told us something about conservation of mass, which is also showing that matter is conserved. So nothing is actually lost. Something that is lost is found somewhere. That's the meaning. So when you watch such video as tagged free energy, please stop clicking such video, because as long as we have that matter is neither created nor destroyed, we cannot have anything like perpetual motion of free energy. But anyway, suit yourself. But they are traps. But when you look at such videos, it gets plenty of views. No problem. Nobody will have such free energy. I'm indirectly trying to show you that nothing have just come to be, and that will not be forever. You can change from one form to another. So, according to Anton Lavoisier, he carried out an experiment to prove this thing, that if you burn pepper, for instance, which is actually this carbon, you react it with oxygen. You have not lost this carbon, rather, you have transformed it in another form of compound known as carbon 4 oxide. So matter is not destroyed, rather matter changes form. How about someone dying? Do death destroy matter? No, death destroys life and function, which helps that life to transform to death. The matter is still there. That's why we still have what we call fossils, and that fossil can turn to some fuel. So you remain there, but in another form. So that is a kind of a everyday life, something that we encounter that I used to explain that. Now, coming to this in chemistry, we don't have any calculation in the law of conservation of matter. Even if we have law, the law of conservation of matter is the only reason why we balance what? Balance chemical equations to make sure that matter is neither created nor destroyed. So they might ask you, maybe because they don't usually ask applied question there. It is here. It is under this balancing chemical equation. That is where you do your atom economy, but not for Nigeria. You do your percentage yield. Is this idea, because matter is neither created nor destroyed. Though the yield might not be 100% as you require, but the matter is not lost. So what I mean is that, let's assume we have, you burnt down this the same carbon and eventually get CO2. This one becomes very simple. You see that the mass you garbaged in is equal to the mass you garbaged out. So because of law of conservation of matter, the sum total of the mass of the reactants must be equal to the sum total of the mass of the product. Let me give you an instance. If we have, during Haber process, nitrogen plus hydrogen to give you is reversible ammonia, balance the equation, there should be 2 here and 3 here. Come on, let's see. You know that hydrogen is 1 and nitrogen is 2. Okay, so if we calculate, sorry, nitrogen is 14, don't mind me, maybe it's saturated. Nitrogen is 14. If we calculate the total mass over here, it must be equal to the total mass here. That's why you must balance chemical equation to show that energy is conserved, matter is conserved, mass is conserved, atoms are also conserved. Okay, so if you check the total mass on the reactant side, let's go. What do we have? We have 14. We are taking case of NO2 times 2, which is 28, then plus 2 times 3 is 6. That is times 1, which gives you 6 automatically. So 28 plus 6 is what? 28 plus 6 will give you 34. My calculator is still working well. So it's expected that the mass we get here is also 34. Ammonia alone is 14 plus 3, which gives you 17, times these 2 here, which gives you 34. So that is it about law of conservation of what? Matter. That's why you must balance chemical equation. And this is why you should also avoid free energy, free motor, all those things, bulb without charging. So please avoid it, because if there is light from a bulb, energy is being spent, and that energy must be exhausted. Another one must be supplied. because we have transformed, and as you are transforming, you are exhausting that source that created it. Okay, we now move on to the last law we'll be handling here, which is Gay-Lussac's law of combining volume. We look at this Gay-Lussac's law of combining volume. Remember, I've treated it in detail in one of my live streams, and you stay tuned to know when I'll go live for this JAMB examination. That's where you join and ask your questions. Okay, Gay-Lussac's law. So I'll state it and take few examples. For you to get the details, please watch that live stream. Lusac's law of combining volume. It says that when gases react, they do so in volumes. When gases react, they do so in what? In volumes, which are in simple ratio to one another, which are in simple ratios to one another, and to the what? And also to the product, and also to the products or products, if only if the products are what? Gases. If the products or the products are gases. So if the products are not gases, there is no rule for that one. So this one is just trying to tell us that as gases do in volumes, so will they do in moles. So if you have 1 mole is to 2 moles, there will also be 2 volumes, 1 volume is to 2 volumes. So it is trying to relate the combination of volume of gases under constant temperature. Now, unless I forget, this thing is only true at the same temperature and pressure. Please, at the same temperature and pressure. So this happens only at the same temperature and pressure. So the Lusac's law, one can still state it in many other ways, but this is the way I decided to say it. You can also say that Lusac's law says that when gases react together under the same conditions of temperature and pressure. I brought my own at last here. You can bring it here. Can bring it first. Under the same conditions of temperature and pressure, the volumes of the reacting gases and the volumes of the gaseous product, if any, are in simple whole number ratio. Yes, they are in simple whole number ratio. That's the moles of the volumes of the gaseous product is also included in the mole ratio, which means I often tell my students, as they do in moles, so would they do in volumes. Let's take a look at sparkling water. Example is this. If we have H2O, not H2O actually, hydrogen, please, sparking of hydrogen plus oxygen will give us what? H2O. Remember, the law is concerned with gas. So over here, my dear, be careful about the state of matter of the product. In this case, I can make my product L, and if I make it L, whatever mole I'll have here will not count. If I make it S, the mole will not count because it's for combining volume, for gases. The law is for gases. So if here is G, it will now count. But you must balance this equation first. If we put 2 here, we put 2 here. So what's the mole ratio? 2 is to 1 is to 2. It means that if we bring them by volume, it will also follow. If here becomes 5 cm cube, here will also be 2.5 cm cube, because half of 2 is 1, half of 5 is 2.5, also is to what? 5 cm cube. Understood? So you follow that mole ratio as they do in mole, will they do in what? Volume. And under this Gay-Lussac, we should be careful, we should be mindful of this term, residual gas and excess gas, unreacted gas. So when we say excess gas, it is the same thing as a unreacted gas. But when we say residual gas, that's the leftover. Residual gas is equal to the total gas left after reaction, which includes the product and unreacted if there is a gaseous product left after reaction. So residue are kind of the total remaining, whether it's the product you want or whether it's the excess that did not react. You get that now? So most times now, residual gas is calculated as what? Residual gas is calculated as unreacted gas plus products plus the gaseous products. So if we have 2 products and only one is gaseous, you take the mole of that gas. You don't mind the other one that is solid, liquid, or aqueous. It is focused only on gaseous product. But in a situation where none of the products are gases, the unreacted gas automatically becomes the volume of residual gas. Okay, so let's take some questions here immediately. Solving it will help you understand maybe more. Endeavor to watch that video. The products and the reactant must have the same temperature. Which one will I lift now? Where can I find this question? Yeah, let's check. Uh, let me check. Okay, this is 2007. 2007 JAMB question number 27. No. Question number 28. Yeah, 28 is what requires that law. It says, what is the volume of oxygen required? What is the volume of oxygen required? So I'll zoom it in more. What is the volume of oxygen required to burn completely 45 cm of methane? So we are going to write the reactants here. There are two reactants we are going to consider and the product. So first of all, you have to write the equation of the reaction. What's the equation? I think I need to move this up a bit. Mhm. The equation of the reaction is we have methane burning, which is CH4 plus what? CH4, equation of the reaction. CH4 plus oxygen. Normal will give you CO2 plus H2O. Remember, if you fail balancing the equation, you have failed it. So there should be two here to compensate the hydrogen. And then there should be two here. And that settles it all because oxygen now is 4, oxygen is 2 times this, for carbon is 1, carbon is 1. So the next thing you write the moles. What's the mole ratio? How to solve it? Mole ratio is 1 is to 2 is to 1 is to 2. And in this case, we are what volume is required at STP. What have I done? I can't see the right things again. 45 cm cube of methane. This is the one I've written. So methane is 45. So they are now asking us, they say at STP, this is going to be gas. They are all going to be gas at STP. Of course, we take it that way. This is the STP, they are all gases. So 1 is to 2. Methane now becomes what? This is 1 is to 2. Which means if methane is 45 cm cube, oxygen will now be what? 1 is to 2. Oxygen will automatically be can just is 90, of course, 90 cm cube. That's supposed to be the answer. But even if you are finding this difficult, you can just say if 1 gave 2, if 1 gave 2, 45 will give x. After every calculation, you find out that x is equal to 45 times 2, which will give you 90 cm cube. So we lift the question back and check if there is any such option. Yeah, option D over here is the answer. Right up as appeared again. So option D, which is 90, gives us the correct answer. So I will struggle now take another example. Let's remove this, bring in this first one. Okay, looking at number 17, it's still the same thing. This should be 2012. Potassium triazole, are you sure? No, this is not Lussac law of combining volume. I have a mix up somewhere. Thank you for watching. It's not all my fault. I think I had two questions, but unfortunately, I don't have. So at this point, I wish to really appreciate you for watching. So thank you so much for watching. Please, if you don't help me expand, how will I continue doing what I'm doing? I very much appreciate. So best of luck in your exam. Succeed.